In this video, I will discuss the deep learning workflow or the recipe for deep learning. In other words, we will discuss how we go from data to a deep learning model. Let's start by discussing the universal process of building a machine learning model. There is a universal workflow of machine learning. Obviously, the first step is to define the problem and assemble the data set. And when you assemble a data set, you also want to understand whether you are doing a binary classification or multi-class classification, or if you're doing a regression problem. So this is primarily what you are deciding at the beginning, whether you want to do a binary classification or multi-class or regression. The next step is to choose a measure of success. That is, how are you going to evaluate the model? What is important for the problem that you are solving? Is it important to have a high accuracy? Or is it important to have recall or precision high? Or do you want higher AUC? Or do you want very low MAE? So what exactly are we looking for in the problem? And that becomes our measure of success. The next step, step 3, is to decide on how we are going to do the evaluation. The standard holdout validation usually works well if you have sufficient data, that is splitting the data into training set and test set, where your training set is further going to be split, development set and test set, and where development set is further going to be split into training set and validation set. Or whether you want to do something more complicated, such as k-fold cross-validation. Now, k-fold cross-validation and then such fold-based validation techniques are useful when you have smaller number of rows or fewer data. But when you have larger data set, the basic holdout techniques works totally fine. The next step, step 4, is to prepare our data set. That is, do we need to normalize or standardize? Are we going to augment the data? How are we going to prepare your data set? So augmentation also comes into play here, and all those techniques that you need to load or prepare the data. The next step is to develop a model that does better than a baseline. So you want to determine the baseline for your problem. For example, if you're doing a binary classification, and if your data is well balanced, that is, if the number of zeros and number of ones in your example are equally balanced, right? Same number of positive and negative, then your baseline accuracy becomes 50%. Right. Similarly, for multi-class classification, you may have a lower baseline accuracy, but you have a baseline metric, baseline value of the metric. So what we want to do here in this step 5, is to develop a model that does better than a baseline, a model that gives you at least 55% or 60%, anything that's higher than what's needed or what the baseline, a random model, would do. And then the next step is to scale up. That is, what we want to do is develop a model that overfits. So we gradually want to make this model more and more capable, complex, bigger, such that we overfit the data set 100%. That is, somehow get 100% accuracy or almost close to 0 MAE on the training set, So we basically want to find out whether or not we can overfit. How big are we going? And then after that, step 7 is to scale down your model and also regularize your model and tune the hyperparameters on the validation set. So this is the standard workflow of building a machine learning model for a problem. Now, the initial steps are pretty clear, so let's focus on the later steps, step 5, 6, and 7. So let's look at step 5, that is how to develop a model that does better than the baseline. Here, the question that we are asking is, can we achieve the statistical power or statistical power using the machine learning model? Here, the question is, Can we build a small model that is capable of beating a dumb baseline or a random predictor? Here's an example. The first example is in the case of MNIST digit classification example, where we have 10 classes, right? Anything that achieves an accuracy greater than 0.1, or if the accuracy is more than 10% approximately, then we can say that the statistical power has achieved by our model. Say if the accuracy is 15%, then it's better than a random dumb baseline, right? In the case of, say, another example would be in the case of, say, IMDb classification, where it's a binary classification problem, then in this case, anything with accuracy greater than 0.5 will do. So in this binary classification problem, anything greater than the 65%, sorry, anything greater than more than 50% can be considered as a statistical power. Now, the next obvious question is, say we try to build this model with the statistical power, and let's say we are always stuck at the baseline accuracy. So let's say stuck at baseline accuracy. Then what do you do? What can you do if you cannot build a model with the statistical power? Here are some debugging techniques. The first thing you want to check is check the last layer's activation. For example, are you using sigmoid for regression? And if you're actually using solving a binary classification problem, do you have something other than sigmoid, right? So you want to check the last layer's activation. You also want to check the loss function. That is, for example, for binary classification, you want to make sure you're using binary cross entropy. And if you're doing regression problem, you have to use MSE, MAE, etc. You also want to check various optimizers. You start with something like RMS prop or NADM, and then with its default learning rate, and then play around with some additional optimizers to see if that helps. The last resort is to use output as one of the input features. Now, this I find is an extremely simple, but the most powerful way of debugging. Most powerful way to debug. And let me explain this. So let's just start with a feed-forward neural network. Say we have a feed-forward neural network that looks like this, that takes inputs from the previous layers, and finally you're predicting, let's say, 0/1, right, a continuous value. And here's my input features. Let's say I have 3 columns, column 1, column 2, column 3, right? So all of these will feed into these neurons, and we're making predictions. Now, in such a network, let's say my accuracy is greater than or equals to the baseline accuracy. That is, my model does not have a statistical power, and it's not doing anything really significant that I can consider like learning. So what do we do? The idea behind this using output as input is, so on this data set, when you have these columns, column 1, column 2, and column 3 as input, you will also have one additional column, which is the output column, right? So this will be the output column that we don't feed as input, but we actually use it to calculate loss with the model's predictions. So the idea behind using input as output, output as input, is to use this additional column, the last column, also as an input column. So now instead of having 3 columns, what we actually have now is 4 columns. So C1, C2, C3, and C4. So our output is still C4, but then we also have C4 as an additional input column. Now, in this way, this is actually dumb or stupid because whatever the model is predicting, we're also feeding in as input to the model. But this is a very good way to sanity test your model. So if as soon as you feed output as input to the model should immediately start giving you 100% accuracy or almost close to 0 MAE, because all that it has to do is understand that the last column has all the input that the model is wanting and map that to the output. So this is a really, really good way to debug if your overall pipeline is correct or not. Now, for convolutional neural networks, this becomes a little bit tricky because in case of CNNs, what we have is an input image volume. And what we are predicting with the deep learning model or CNN model is one single value, right? And this is my output. So then how to use output as input in case of CNNs? Well, what we can simply do is add one additional channel to the input. So one new channel with all values equal to the output. So it's a flat channel where all the values in that 2D matrix are all, let's say if the correct label is a 1, then we want to have all of this as 1. And if the label is 0, then we want to have all of these values as 0. So this way, the model has access to the correct label as an additional channel. So this is another way of debugging convolutional neural network if you are getting very low statistical power, to make sure that the pipeline is working and everything is in place. So in the next step, the task is to scale up, that is develop a model that overfits. So what do we do now? So far we obtain a model that has a statistical power. What next? Now what we want to do is find out if our model is sufficiently powerful to learn more patterns. In other words, does it have enough layers and parameters to properly model the problem at hand? That's what we're asking here. Now, to figure out if you can overfit, you have to overfit, right? How do you know that you've overfit for a data set without overfitting? There's no way out. So you actually have to, let's say, for example, in x-axis, I have the number of parameters of my model, number of parameters, and let's say this is number of layers, number of neurons in each layer, and so on. And let's say in y-axis, I have my accuracy on the training set, right? So I have to keep in, let's say, and this is 1 accuracy and this is 0, 100% over here on top. So then I have to keep increasing this to the point where I actually start getting almost close to 100% accuracy to know how big of a model is an overkill, right? So we want to find out how large model do we need to overfit. We don't want to overfit, but to sit in between overfitting and underfitting, we have to overfit at least once to find out how big of a network do we need to overfit. So how do you overfit? We can simply add more layers, make the layers bigger, that is increase the number of neurons in each layer. In case of CNN, increase the number of filters, and also train for more epochs. And what we want to do is monitor the training loss and validation loss and accuracy and MAE. So what we want to do is not just look at accuracy, but also look at the training loss. If I make my model bigger and bigger, do I see decrease in loss every epoch? Now, when you see that your model's performance on the validation dataset begins to degrade, you've achieved overfitting. So maybe in the first epoch, E1, your training accuracy is 80% and your validation accuracy is 70%. Maybe in your epoch 2, you have maybe training accuracy goes to 90% and the validation accuracy goes to 80%. Epoch 3, let's say training accuracy becomes 93% and the validation accuracy becomes, let's say, 79%. So now I can see that the validation accuracy is starting to fluctuate, right? But then the training accuracy in the next epoch will be maybe 95%. And so this will keep increasing. Training accuracy will keep increasing, but the validation accuracy will, at the beginning, may show trends of it starting to improve, but then later it will wobble a lot. So as you start to see a drop in validation accuracy, so if we, let's say, maybe plot in x-axis epoch and in y-axis, let's say, loss, then at the beginning, the training loss may be very low, very high, and then it'll gradually keep going down. But the validation loss maybe start somewhere here or somewhere here, and then it will start going down, and then later you'll see that it will try to go back up again. So this is, after this point, is when you know that you've started to overfit. So we want to get there once to understand when and how we can overfit. The next step is to regularize the model and tune hyperparameters in order to get highest accuracy on the validation set. So we repeatedly modify your model, that is, increase the number of layers, number of epochs, number of neurons in each layer, and then train each of these models and evaluate on the validation set. So here it's important that we focus on the validation set. And we want to repeat until the model is as good as it can get on the validation set. So here, what are the things we can play around with? So here, the debugging techniques or the things to try out are add dropout in between your layers. Try different architectures. For example, maybe you want to use standard plain CNN. Maybe you want to try ResNet. And so on. So we have to try various different architectures and see which one helps. Also, we can try adding L1 and L2 regularizations. We can try different hyperparameters such as the number of units per layer, the learning rate of the optimizer, etc., or even find a different optimizer to find the optimal configuration in which we get the highest accuracy on the validation data set. So here, the main focus is on the validation set. So focus is here. And optionally, you can also add new features or remove features that don't seem to be informative. Now, once you have developed a satisfactory model configuration, then the last task is to train your final production model on all the available data, training and validation, and evaluate it one last time on the training set. Because once you have tested on the training set, you don't want to come back and retrain the model. Practically, you may do it a few times, but technically, the whole idea is not to use the test data to tune your model. That is, we don't want any information leak from the test data into your training model. So maybe at the beginning when you're trying it for the first time, you may find something really funny, or maybe your test data set wasn't shuffled at all and you realize that you can go back and retrain. But you don't want to be doing this repeatedly over and over again such that eventually your model is tuned towards test data set.